The Earth is ringed by two zones of high-energy particles. These areas are now called the Van Allen radiation belts in honor of the physicists whose work led to their discovery. The existence of the Earth's radiation belts presents a very serious hazard to future space travel. What is the intensity of this radiation? What does it consist of? How much shielding will the first space travelers need in order to penetrate these deadly areas of radiation safely? As a result of a unique experiment, some of these questions have been answered. And to tell us this remarkable story, we've invited the two scientists who conceived and carried out this project. Our first guest is the leader of the Nuclear Effects Group for the University of California's Lawrence Radiation Laboratory, located at Livermore, California. I'd like to have you meet Dr. R. Stephen White. Welcome to Science in Action, Steve. How are you?
Thank you, Earl. It's a pleasure to be here.
I would like to know what it was that gave Dr. Van Allen the first clue to the existence of these radiation belts.
The first clue, Earl, was furnished by a raccoon.
Well, I know raccoons, but raccoon, I'm not quite sure.
Well, it's quite an appropriate name, Earl. A raccoon is made up of a balloon and a rocket hung from that balloon, and they were launched from the deck of a ship. Dr. Van Allen, back in 1953, was doing some cosmic ray research in the vicinity of the northern auroral zones. You know where the northern lights are?
Yes.
And during some routine experiments, about 30 miles up, he ran into an area of radiation far stronger than anyone had expected.
Well, at the time, did he have any idea what the cause of this radiation was?
No, it puzzled everyone. Further experiments were needed at higher altitudes than the raccoons were capable of reaching. The chance came in 1958 when Explorer 1 went into orbit, and it carried cosmic ray detectors and a transmitter designed by Dr. Van Allen's group.
Over here in this next section, we have sketched the orbit of Explorer 1, and I notice that down here it's very close to the Earth, whereas up here it's quite far apart. That is quite a distance from the Earth. Perhaps you could put that mileage indicator 200 miles at that point, and then I will put this one up here, which indicates 1,500 miles from the Earth at this section.
Well, this is what brought the first surprise, Earl. At the 200-mile level, the counting rate was just as expected. But as the satellite went to higher altitudes, above 600 miles, the radiation increased and then dropped to zero.
Well, that would seem to indicate that perhaps there was no radiation up here, and yet everything I read has said that the further you go out, the more radiation you pick up.
That's right, Earl. That's just what happens. And this left Dr. Van Allen with only one explanation. He quite naturally assumed that his detectors weren't working properly. The chance came to check this experiment when Explorer 3 went into orbit with equipment similar to that carried by Explorer 1.
And what kind of results did he have that time?
Just about the same thing. At the lower altitudes, the counting rate was low. But at the higher altitudes, the counting rate went up and then mysteriously dropped to zero.
Well, then either the equipment wasn't working properly, or perhaps there just wasn't any radiation up here.
Well, as it turned out, Earl, neither was the case. And I'll show you on this next demonstration here exactly what happened. This is a Geiger counter designed on the same principle as that used by Dr. Van Allen in the Explorer flight. As we go on up to 2,000 miles, we have here with us Joe Hilson from the effects group at Livermore, who will put in the cobalt-60 source, which will serve as a source of radiation for the experiment.
That goes right at the top of the...
That's right in the middle of the belt. You'll notice the counter went up here as he stuck that source in.
Yes.
Now, I will turn on the sound here, and we'll imagine that the Explorer is mounted in, that the counter is mounted in the Explorer satellite, and you can hear the counts here, you can hear the sound, and you can also notice the reading on the meter. Now, I'll start the takeoff here, and you can see the radiation mount as the satellite goes to higher altitudes. And you'll notice it gets pretty high here. It goes up just as we would expect as it gets closer to the radiation source.
This is the same thing that happened in Dr. Van Allen's experiment.
Exactly. And now we'll jump above 600 miles, and we'll see what happens when we get closer to the source of radiation.
Uh-oh, there it goes back down to zero again.
Yes. The explanation for this is that the satellite had gotten into an area of radiation so strong that the counters were completely jammed. Now we'll return the satellite back down to the lower level, away from the radiation.
In other words, it went back to zero and then came back up again.
That's right, and you can see it's still very high there, Earl. Now we'll go on down to the lower altitude yet. And you can see the counter is now working normally, just as if nothing is wrong.
Well, then it was a question of equipment which was designed to be very, very sensitive, but couldn't take the amount of radiation which was in this area way up above the surface of the Earth.
Exactly, Earl. Dr. Van Allen had run into an area of radiation far stronger than he had expected, and his counters just weren't designed to detect such strong radiation. The confirmation of this discovery came with Explorer 4. The lunar moon rocket, Pioneer 3,
Yes.
went out 65,000 miles and not only confirmed these discoveries, but also found a second radiation belt farther out.
Well, to find out the relationship of these two radiation belts, we have set up over here in this next section an exploded arrangement of what this might look like, of course, with the Earth right here in the center.
You can see here there are two distinct belts, Earl. Both surround the Earth like huge donuts, with holes at the top and the bottom. Now, the inner radiation belt has its maximum intensity at about 2,000 miles out, while the outer radiation belt has its maximum intensity at about 10,000 miles.
Now, when you talk about intensity of radiation, what is this going to mean to the first person who takes off from the Earth as a space traveler?
Well, Dr. Van Allen estimated that the intensity in the inner belt was about 10 roentgens per hour, and the intensity in the outer belt was several times that. The human body should not be exposed to more than about 1 Roentgen per month over an extended period of time.
Well, obviously, then, some kind of protective material is going to be required to enable this person to make the flight.
Yes, the first traveler will probably go into orbit at something like 400 miles from the surface of the Earth.
This would be the radiation belt right here.
That's the lower radiation belt, and there are about 200 miles separating the radiation belt and the orbit of the space traveler. But to go farther out, for example, if he wanted to go to the moon, there are two possibilities. Now, let me go back to this diagram to show one possibility. That would be for the rocket to go out through one of the holes in the donut, but to come back in through one of these holes is a different problem, and it would be very difficult to do without passing through one or both of the radiation zones.
Well, then, if, as you say, he's going to have to go through this radiation belt to get back to the surface of the Earth, or perhaps even to go out, then he's going to have very, very good protective materials.
That's right, Earl. In order to determine the amount of shielding required, it was necessary to obtain more information about the nature and the energy of the particles that cause the radiation.
To find out about that, I'd like to go at this point and join one of your colleagues at the laboratory. You and your colleagues there at the laboratory seem to me to have had a tremendous job in trying to figure out all the details of this radiation belt.
Well, the first step, Earl, was to figure out a method of getting the desired information about the inner belt.
I'm wondering, now you say inner belt just a moment ago, and we're over here, we were talking about two belts, an inner belt and an outer belt. Why do you specify an inner belt?
We had good reason to believe that the radiations in the inner belt are more penetrating than those in the outer belt. So by shielding against the inner belt, you're automatically safe in the outer belt.
What kind of equipment do you need to get the data you require?
Here it is, Earl.
You're fooling. That's all. This is the entire piece of equipment?
This little stainless steel box contains what we call an emulsion stack.
Can we open it?
Here, I'll open it for you. Actually, each of these little squares is a piece of film. They may look a little different to you at first because the film we use